Now, we studied about the conditions A and B. What about liquefaction? When does a gas liquefy to form a liquid? So, the basic conditions which we need for liquefaction are high pressure and low temperature. Basically, we need the molecules of the gas to come close enough so that they do not repel, but their attraction is so strong that they remain bounded and become a liquid. So, for that, we define some critical conditions. Critical conditions are those which are characteristics of the liquefaction stage. Okay, so we have three critical conditions, which are the critical temperature, the critical pressure, and the critical volume. So let's go into a little bit of detail about these critical conditions. So the critical temperature, by definition, is the minimum temperature above which a gas cannot liquefy. So basically, what do we mean by critical temperature? It is that temperature, that limiting temperature above which, if the temperature is increased, the gas cannot be liquefied, however high pressure you may apply. And below the critical temperature, liquefaction is always possible by applying the appropriate amount of pressure. So the critical temperature has an expression in terms of A and B, and that expression is 8A divided by 27 RB. Now, for an ideal gas, A is 0, therefore critical temperature would also be 0. Now, what does 0 critical temperature mean? 0 Kelvin is not something which is attainable, right? It means that for an ideal gas, there is basically no such practical temperature above which it would not liquefy and below which it will always be liquefied, because an ideal gas lacks the intermolecular forces of attraction. So there is no temperature below which it will always liquefy. Therefore, the critical temperature is such that above it all temperatures are attainable and the gas won't be liquefied in case of an ideal gas. Now let's talk about the critical pressure. Critical pressure is defined as during liquefaction of a gas, the pressure attained at the critical temperature is called the critical pressure. And if we try to similarly define critical pressure, it is A divided by 27 B square. Then comes critical volume. Critical volume is the volume occupied by the gas at the critical temperature. This is called the critical volume. And this too has a similar expression which is given by 3b. Now, in terms of these critical conditions, if we talk about a condition for liquefaction, like a limiting case condition, that after this liquefaction will always occur. So, for that what we do is that we know for liquefaction the temperature should be below the critical temperature, right? Because if the temperature rises above the critical temperature, the kinetic energy of the molecules is so high that they cannot be brought close together and be made to attract. And the pressure should be greater than the critical pressure. Then only would we be able to liquefy the gas. Right? The temperature is below the critical temperature and the pressure is above the critical pressure. So at critical conditions, let's see what the value of Z comes out to be. Z was PV divided by RT, right? So at critical conditions, the pressure is PC, the volume is VC, and the temperature is TC, correct? Let's just plug in the values. Now PC is A divided by 27B square. VC is 3B. There is R, and TC is 8A divided by 27 RB. So let's start cancelling things out. We have a B here and a B here. This gets cancelled with B square. R gets cancelled and A also gets cancelled. Now 27 gets cancelled with this 27 and we are left with 3 by 8. So the value of Z, that is the compressibility factor at the critical conditions, is 3 by 8. And as you can see, it is less than 1, which implies that liquefaction is occurring. So, at critical conditions, what we can conclude is that PC Vc is equal to 3 divided by 8 R. This is an expression which can be used at the critical conditions.